One more thing that we can do with the chain rule and partial derivatives, now that we have those tools in our pocket, is actually reconsider the idea of implicit differentiation from way back in Calculus 1. So just as a reminder for what's going on here, consider this sort of problem. Suppose that we know that y to the fourth plus x times y minus x cubed plus x plus 2 was equal to 0. And, standard Calc 1 problem would be find dy over dx. So the way that we would do this using implicit differentiation is that, and once again, what I'm doing right now is purely a Calc 1 problem for our purposes. I take the derivative, this is a normal derivative. We're thinking of y as a function of x here. We take the derivative with respect to x of both sides here. And what do we end up with? So the derivative with respect to x of y to the fourth would be 4y cubed, but we're taking the derivative, the underlying function here is y. So we need to multiply by dy dx. Plus, product rule here. The derivative x, it's this times the derivative of this plus this times the derivative of this. And so we would end up with the derivative of x is 1 times y plus x times the derivative of y with respect to x, and that's just dy dx, minus the derivative x cubed with respect to x, that would just be 3x squared, plus 1 plus 0 is equal to 0. And then our next step here, our next step here would be to rewrite this. We want to factor out dy dx. We're going to treat dy dx as a single variable and solve for it, basically. So dy dx times 4y cubed plus x is equal to, let's move all of this to the other side, 3x squared minus y minus 1. And so our final steps would be, dy dx would be 3x squared minus y minus 1 over 4y cubed plus x. So everything on this slide, everything here, this is all review. This is stuff that you've seen before. This is stuff that you already know. But let's just take a moment here to appreciate this, to appreciate this a little bit more. So what I want to do, now that we're in chapter 14 of the textbook, now that we have the language of functions of more than one variable going on here, I want to suppose that we say f of xy is y to the fourth plus xy. This is the left side of the previous equation, so our equation is really f of xy is equal to 0. Okay, let's take partial derivatives of f with respect to x and with respect to y. So the partial derivative of this function, big F of xy, with respect to x, would be 0 plus y minus 3x squared plus 1. And the partial derivative of this with respect to y would be 4y cubed plus x, and that's it. So here's our x partial derivative, here's our y partial derivative. So take a good look at these two things. And now take a good long look at the dy dx that we came up with in our previous slide here. And, is there any similarities? Can you go between this and this? And the thing that you should notice here, let me recopy dy dx, is 3x squared minus y minus 1 over 4y cubed plus x. Well, the denominator, that's just the y partial derivative, and the numerator is the negative of the x partial derivative. So dy dx is the negative x partial derivative divided by the y partial derivative. And so what's going on here? This turns out to always hold. This is not an accident. This will always hold. And we can actually get this formula here. Let me recopy this. So if f of xy is equal to 0, then dy dx is equal to negative the x partial derivative divided by the y partial derivative. Now, how do we come up with this? What we're going to do is that we're going to use the chain rule here. And so taking the derivative of big F with respect to x, using the chain rule with x as the independent variable. So the thing that will happen is that we can say that the partial derivative of big F with respect to x times the partial derivative of x with respect to x. So like this x is playing two different roles, the intermediate variable and the underlying variable, plus the partial derivative of f with respect to y times the partial derivative of y with respect to x here. It's going to equal the partial, take any partial derivative you want of the right, you're going to get 0. Well, this derivative x with respect to x is just 1, and this I really probably should write it without the partial derivatives, dy dx here. And then these two expressions here, this is our x partial derivative plus our y partial derivative. This plus this times this is equal to 0. And if we solve for dy dx, you end up with exactly negative x partial derivative divided by the y partial derivative. And so this new little trick here, has given us a new way to do implicit differentiation. So going back to Calc 1, Calc 1 kind of problems. If you had known how to do partial derivatives in Calc 1, well, you could have, an alternative way to crunching through everything with implicit differentiation is just using this formula. Okay, I think that's a good place to wrap up this video. We'll do one more video on this implicit differentiation stuff, kicking it up to functions of x and y and z now.